All right. So for chapter 5, we're going to be going or talking about force and motion. Up to this point, we've done a lot of discussion regarding vectors and components of vectors. That's been kind of a necessary part to understand before we get going into force. Because we're going to be dealing with components of vectors pointing in certain directions, and we'll need to be able to analyze which part of a force vector is going in which direction. So, all right. So we're going to be looking over Newton's first as well as his second law, and we're going to be discussing a lot of these objectives here. I'm just going to list them here because if I start talking through them, they'll kind of get lost. And it's better to kind of focus on these things one at a time and watch the concepts build. So what is a force? What do I mean by that? Force is going to be a pushing or pulling that is acting on an object. In other words, if you push on a book or something like that, or if you are pulling on a string that is attached to something else, those forces are going to be represented with, or those actions are going to be represented with force. Forces are going to cause acceleration of an object. In other words, we're attempting to change the speed of an object. And what we're going to be focusing on here are Newton's 3 laws of motion. If you actually go back and you read how Newton wrote these things up, it's not really that clear. So going through and just having a summary of what these things mean is almost better than trying to go back and read what Newton had written. I mean, if you're ever bored and you want to do it, that's certainly something to do, but generally the summations we'll have here in these discussions will suffice. So Newtonian mechanics is going to be valid for everyday situations. What we mean by that, they're going to be valid for cases in which we're not approaching the speed of light to within a certain degree. Most of the everyday things that we run into are going to be nowhere near what the speed of light is. And because of that, this model of reality will work just fine. It's not going to be valid for objects that are on the atomic scale. It's just we can try working the laws at that point that it just doesn't give good results, so we don't use it at that scale. And it is also viewed as an approximation of general relativity, which we're not really going to concern ourselves with too much in this course. So before we came along with Newtonian mechanics, we had thought that the universe works, that some force was keeping things moving, and that the natural state of objects were going to be at rest. So that's not really the best way to look at things. If we took a look at a frictionless surface, it doesn't slow down an object because there's no friction there to stop an object. So we don't need a force on a frictionless surface to keep it in motion. So, first law, if no force acts on a body, then the body's velocity cannot change. In other words, it's not going to accelerate. So if you have an object. Let's see if I can draw. So we've got this object right here, and it is moving at a particular velocity. And we'll just say that velocity is 5 meters per second. If there's no force acting on that particular body, then the body's velocity continues to move at that speed. It doesn't change. An acceleration, or in this case, deceleration, does not occur. This body's going to stay in motion indefinitely. Something has to come along and to change that particular velocity. So that's Newton's first law. In other words, change in velocity is not going to happen until another force is applied. So how is it measured? Forces are measured in terms of newtons. And the unit for newtons is going to be N. 1 Newton is going to be 1 kilogram meter per second squared. So the acceleration of a mass is proportional to the external force, and forces, of course, are vectors. What is a net force? Well, the net force is going to be the sum of all forces on an object. So what does that really mean? So let's take another object here. And let's say it is subjected to a force going this way, and it's also subjected to another force going this way, but maybe this one isn't quite as strong. The net force is going to end up being something that maybe is not quite as strong, but still pointing in this particular direction. It's going to be the sum of this vector as well as that vector. So a net force has the same impact as a single force with identical magnitude and direction. And basically what that means is if I'm on one side of an object and I'm applying 100 newtons of force, and let's say, Braden, you're on the other side and you're applying 200 newtons worth of force, the direction and magnitude of the net force is going to be the same thing as if I weren't pushing at all and you were just pushing with 100 newtons of force. Does that kind of make sense?
That makes sense.
Okay. So restated. If no net, there we are. Hey, Giselle. I figured it takes time for the camera and mic and everything else to come on. So for Newton's first law, if no net force acts on a body, then the body's velocity cannot change, and so the body cannot accelerate. So if the net force is 0, what that means is there's nothing being applied to that body that's going to cause its acceleration to change. You can have two very powerful forces on either side of an object that are pushing on it, but if they're pushing on it equally in both sides, the net force is the same as if nothing was going on. So how you doing, Giselle? I see the mic is on, but I don't hear anything. That's okay. All right. So Newton's first law is not true in all reference frames. So there's something here that we need to discuss. What an inertial frame, an inertial reference frame. So this is going to be classified as a reference frame in which Newton's laws are indeed valid. Some examples of that: a frictionless puck pushed from the North Pole viewed from space, that's considered to be fine. The same situation is viewed from the ground. Now, the funny thing is here is over long distances, the ground is not an inertial reference frame. The reason is that uh, the ground is not going to be moving at a constant velocity relative to, say, the same point in space. That's the difference. It's not something we're really going to get into that much, but that's the key meaning behind it. So Earth's rotation causes an apparent deflection. In other words, as this is rotating, that puck is not necessarily going straight down. There's actually a little bit of a curve to it. So there's more involved with that. We're not going to go quite that far into it. But for now, for inertial reference frames, that's where we're going to be focused. So in general, we're going to assume that the ground is in fact an inertial frame. It's an inertial reference frame. So we're going to have 6 arrangements of vectors here. So which of these figure 6 arrangements correctly show the vector addition of forces 1 and 2 to yield the third vector? In this particular case, A is not a correct arrangement because we've got one force going here, one force going there, and we've got a resultant going from tip to tip. That's not a correct arrangement. And neither is B, because again, we've got the resultant going from tip to tip. So that's not going to work. C, however, is, because we've got one vector and another vector that are going from tail to tip and then tail to tip. Our resultant vector goes from the tail of one vector to the tip of the other. Same thing holds true here with D. Both E and F are not considered to be arrangements that correctly show the vector addition of forces. It's that tail to tip kind of arrangement that it's looking for. Now, it does say that E here happens to be a correct answer. And in this particular case, it is saying I've got a vector at one point here that's pointing this way. I've got a vector at one point that's pointing this way. This resultant vector right here lies along those same lines. So it does consider E to be a correct answer. F in this particular case is not, because that resultant vector starts here and points down, and neither of the two vectors being added together point in this direction. Okay, that leads us to this particular concept. What is mass? The mass of a body is the characteristic that relates a force on the body to the resulting acceleration. This may come as a surprise to you, but mass is a measure of a body's resistance to a change in motion, but it's not the same as the weight. So for instance, if I were to weigh myself here on Earth and I were to have determined that I'm 100 kilograms, if I were to go to space, the gravitational pull that I'm experiencing there has vanished. So my weight would be nothing. The mass that I would have, however, would still be 100 kilograms. So mass is going to be something that is a concept. It's a concept that's a little bit different from weight. And since mass is a measure of a body's resistance to change, it's going to be considered to be inversely proportional to acceleration. So if I were to apply an 8-Newton force to various bodies, say 1 kilogram, 2 kilograms, half a kilogram, so on and so forth, what is going to be the acceleration? Well, let's get my drawing tools out here. Force in this case is going to be mass times acceleration. So let's take a look at the first problem. I know that the force being applied is 8 newtons. I know that the mass that I have is going to be 1 kilogram. I also know that's going to be multiplied by the acceleration. So if I solve for A, I get 8 newtons divided by 1 kilogram. And since a newton is a kilogram meter per second squared, that means get my units right. The acceleration is going to be 8 meters per second squared. So that would be for the first problem. For the second problem, if the mass is 2 kilograms, again, the force is equal to mass times acceleration. Again, I have 8 newtons of force. The mass is 2 kilograms. I don't yet know what the acceleration is. If I solve for A, I get 8 newtons divided by 2 kilograms. So my acceleration is 4 meters per second squared. Does that kind of make sense?
Yeah, I'm all good here with that.
Okay, good. Giselle, how about you?
Yeah.
Okay. If I'm going too slow, you just don't hesitate to tell me. I don't want to bore you, but at the same time, I do want to make sure that you got it. So, Newton's second law. The net force on a body is going to be equal to the product of the body's mass and its acceleration. So as I had just finished typing out in that example, the net force is going to be the mass times the acceleration. So the acceleration obviously is going to have 3 dimensions here. I'm going to have the acceleration in the x direction, acceleration in the y, and acceleration in the z. So my net force in each of those directions is going to be the mass, which is the same in every direction, times the acceleration in that particular direction. And if we're looking at the sum of forces, what we're going to do is we're going to take those forces and we're going to combine those forces acting, those components acting in the same direction. So it's not going to be just a blanket addition no matter how those forces are pointed. We're going to have to figure out what part of the force lies along which particular dimension. So as I had mentioned before, if I have an object, let's say a big box sitting on the ground, And let's just say I've got okay, Braden, this is you right here, and you're pushing on this box. And over here, Giselle, I've got you. And you're pushing back on that box. Braden, you're pushing here, and you're pushing with 10 newtons of force. Giselle, you're pushing back in the opposite direction with the same amount of force. What's going to happen to that box?
It's not going to move because the forces cancel out.
That's right. The net force is going to be 0 because the amount of force being pushed or presented this way is going to be equal to the amount of force presented in that direction. Okay. Here's some interesting dimensions of force and mass and acceleration. And I'm not sure if you've heard of these yet or not. If you're looking in the SI system, your force is going to be measured in newtons. CGS, it'll be dynes. And if you're looking at the British system, the imperial system sometimes it's called, that's going to be called pounds. Mass is going to be something different. It's going to be kilograms, grams, and I don't know if you've ever heard this before or not, but a slug. That's the mass in the British unit of measurements. Acceleration for the SI is going to be meters per second squared. CGS is centimeters per second squared. And British is going to be feet per second squared. And you can see down here, 1 dyne is going to be 1 gram times 1 centimeter per second squared. A pound is going to be 1 slug times 1 foot per second squared. Okay. To solve problems with forces, a lot of times we do something called a free body diagram. In other words, the diagram will be drawn, but what we're going to do with a free body is we're going to abstract everything and just turn it into forces. So the only body shown is the one we're going to be solving for. So let's see if I can zoom in here. So we have a hockey puck here, and it's got a force, and it's pointing in the X direction. This is a free body diagram. Rather than sit here and draw the puck and the surface that it lies on, we're just going to make it a point, and we're going to label it as puck. And then we're going to have the force drawn in this particular direction. That is going to be considered a free body diagram. If we look here at 2 forces acting on the puck, we're interested in the net acceleration, but if we want to draw a free body diagram, we take the puck and the ground, have it disappear, just have a little dot there, and this is going to be a free body diagram of the net forces. If we have an example here in part C, where we have one force that is being pointed in the negative horizontal direction, and then we have another one that is pointed down and in the positive direction. all we might be interested here in is the horizontal part of this particular vector that's pointed down. If we go to the free body diagram, this is how we redraw it with that object removed. All right. So we've got Newton's first and second laws. Going through the checkpoint here, we've got a figure that shows two horizontal forces acting on a block on a frictionless floor. If a third horizontal force, F3, also acts on the block, what are the magnitude and directions of force 3 when the block is stationary, and then when it moves to the left with a constant speed of 5 meters per second? So what this is saying here is that the force is going to be 2 newtons to the left in both cases. So let's kind of work through that. We've got force number 3 here. We're not exactly sure how it is acting on this particular block, but what we do know is that in part A, if this block becomes stationary, how must that force be applied? Well, here we've got, let's try this again. I'm going to call this right here, I'm going to call this F1, and that's going to be equal to 5 newtons. Over here, I've got another block. This is going to be F2 is equal to 3, and that would work if I actually have this working with me here. F2 is equal to 3 newtons. Okay. So let's take a look at part A. If the block is to be stationary, what has to be true about these particular forces? Or about the net force, I should say. If the block is stationary, what's going to be true about the net force? What's the net force going to be equal to?
Shouldn't it be 2 newtons to the?
I'm just talking about the net force. What's the net force going to be if the block is stationary?
0 because it's not moving.
That's right. 0 newtons. So for force 3, which direction and how big or how large does that force have to be to counterbalance the 5 newtons this way and the 3 newtons this way? Well, net force currently is going to be equal to, and I'm just going to call going to the right positive and going to the left negative. 5 newtons minus 3 newtons. So what's the net force currently? Be 2 newtons, right? In which direction is that pointing?
To the right.
That's correct. So to make the block stationary, force 3 must be how big in which direction? Any idea? It's going to be 2 newtons pointing which direction, left or right?
Left.
Left.
Should be pointing to the left, which is not kept. It is left. There we go. The reason that is true is because we have to have another force pointing this way in order for the sum of these to equal 5. That means force, this third force has to be 2 newtons this way. So if I add these two together, I come up with 5. That counterbalances the 5 newtons that are pointing in this direction. Okay. So now, part B is asking what are the direction and magnitude of force 3 when the block is moving to the left with a constant speed of 5 meters per second. Well, there's a trick here, and it may not be easy to see immediately. You see that? There are 2 key words there, constant speed. If something is moving at a constant speed, is the object accelerating or decelerating?
Neither.
That's right, neither. So in order for it to move at a constant speed, the forces on it has to be what? What do the net forces have to total up to be?
Would it be 0 so it's not accelerating?
That's right. In other words, the object has to be experiencing no net force. It can still move at a constant speed. That's not a problem. If it's stationary or if it's moving, I mean, that technically is 0 meters per second. But if it's moving at a constant speed, which, 0 meters per second would qualify, it doesn't really matter what that speed is. The fact that it's constant does matter. And that's why on this particular slide, it's saying that the third force here has to be 2 newtons to the left. Because when that's the case, the net force on this is equal to what? What's the net force out of this? Should be 0. So when something has a net force on it of 0, it's going to continue to either remain completely stopped or remain moving at a constant speed. Does that make sense?
Yeah.
Okay. It's a little twisted there, I grant you, but since we're talking about force, and force is acceleration, which is a change in the speed, then that's, as long when you remember that, then this makes a little bit more sense. Okay. So a system consists of one or more bodies, and any force on the bodies inside a system exerted by bodies outside the system is an external force. So the net force on the system is going to be the sum of external forces. So forces between bodies in a system are going to be considered to be internal forces. In other words, if you're part of the group already, that's going to be considered to be an internal force, an internal dynamic. If you're coming in from the outside and you're exerting a force, that's considered to be external. All right. Now we'll discuss a little bit about free bodies and acceleration. So everybody's pretty much familiar with gravity. You have an idea as to what gravity does. It's a pull that acts on a body when it's directed towards a second body. So in most of the cases, when it comes to Newtonian physics, we're going to consider that second body to be the Earth. And when you do that, you end up with certain values here that you use constantly. Okay, so if you're in free fall, in other words, you're moving in the y direction with no air resistance, then minus F subscript G is going to be the mass times minus G. In other words, the acceleration due to gravity, or the force of gravity is going to be equal to mg. Anybody remember what the value of G is?
$9.81, right?
And what are the units?
Newtons?
No, this is going to be acceleration.
Oh, meters per second squared.
Yeah, meters per second squared. Good. So this force still acts on a body at rest. So in other words, wherever you happen to be, your laptop is sitting still on your desk, right? It's still being subjected to the force of gravity. It's just what's happening is that your laptop is pushing on the desk and the desk is pushing back. And it's pushing back just enough such that your laptop is not having its speed changed. Sometimes you will see this written as a vector, where the force due to gravity is going to be minus F, F sub G times J. Usually J is used for motion in the y direction. And since F of G is equal to mg, you can go ahead and substitute that in. So weight. So weight is going to be the name given to the gravitational force that one body, like the Earth, exists on an object. It's going to be a force that's measured in newtons, and it's going to be directed down towards the center. So the weight of a body is going to be equal to the magnitude F of G of the gravitational force on the body. So to relate weight to mass, consider an apple in free fall. The only force on the apple is going to be the gravitational force, and that results in acceleration of G. So if you apply Newton's second law, basically you're saying the net force is equal to mass times acceleration. In this case, the acceleration that's being applied is going to be the force of gravity. That's going to be equal to the weight, and acceleration is going to be equal to the force of gravity. So force of gravity is equal to weight is equal to mg. So in other words, the weight is going to be equal to mass times the gravity. So measuring weight, you can obviously use a balance to compare a body to known masses. In other words, you know what a particular mass is. You know how it changes on the scale. If you see something that changes relative to that, you can determine what the weight is. Weight must be measured when the body is not accelerating vertically. So in other words, you can do this while you're in the bathroom, which generally your bathroom is not going to be accelerating in any direction. Why does it say here that you can do it on a train?
Because you're not moving vertically.
That's right. Yeah. The dimension in which you're moving is not up or down. That's why it mentions here you can't really measure the weight in an elevator if it's moving one direction or the other in a vertically. Okay. Here's a concept that is going to prove useful here in the next chapter. It's called the normal force. So if you're standing on a surface, let's say you're standing there at your computer, the pushback on you from the surface is going to be considered to be the normal force. Normal means perpendicular. So in other words, if you're standing up and you are standing on the floor is going to be perpendicular to your body. And another word for perpendicular is going to be normal. So that's why they call it the normal force. So when a body presses against the surface deforms and pushes on the body with a normal force that's perpendicular to the surface. You may not be able to see this deformation, but it's there. So here's an example. The normal force is the force on the block from the supporting table. In other words, the table is pushing back. And you can see that the block has the force of gravity working on it. So if you look at this particular description, you're seeing that the block, of course, is just sitting on the table. It's not moving. And if it's not moving, it's not accelerating. So it's experiencing two forces. You've got the force of gravity, which is trying to pull it through the table, but the table is strong enough to exert a normal force in the opposing direction such that the block is not moving. What is the name of this diagram right here?
Is that a free body?
That's right. We have taken the block, we have removed it, and now all we're doing is we're showing the net forces on it. And what can we say about the normal force and the force of gravity? What can we say about those two?
They cancel each other out.
That's right, they're equal. They're moving, they're forces that are equal, but they're in opposite directions. If they were unequal, then the block would be moving one direction or the other. So let's say you've got a block here. normal force for a block resting on a horizontal surface that is accelerating vertically. In other words, it's if you're taking that table and for whatever reason decide you're going to throw it up in the air, or if you're going to take the table and say decide to throw it down a couple of stories, that would be accelerating that table, which is where this AY is coming from. The normal force would depend on whatever that acceleration is. If, however, in the case that we just looked at, where it's just vertically at rest, it's not going anywhere, then as you had answered, the normal force is going to be equal to the mass times gravity. So in figure 5.7, let's make sure that we see that. So in this figure right here is the magnitude of the normal force greater than, less than, or equal to mg if the block and table are in an elevator moving upward at a constant speed and at an increasing speed. If it's moving at a constant speed, it would just be equal to the mass times the gravity. Because again, the constant speed means what? There's no what?
There's no net force.
Well, there's always a net force, but there's no acceleration. That's the word I was looking for. So in other words, it's not speeding up, it's not slowing down. It's just moving at a constant speed. Now, let's change that to an increasing speed. So the elevator is moving upwards at an increasing speed. So is the table having to push harder to keep the block from moving, or is it having to push less? Or maybe it's not having to change anything at all. So if I'm in an elevator and I put a block on a table and the elevator starts moving upward, is that table having to apply more force to keep the block where it is, or is it having to apply less force?
Apply more force because it's accelerating up.
That's right. And that's why the answer here is greater than mass times gravity. If it were to move down, do you think it would have to apply more or less force? If the elevator,
Just less force.
that's right. Yeah, if the elevator were moving down, it would be having to apply less force. Okay, now friction. This occurs, everybody's familiar with friction. Anybody ever had somebody rub a burn onto their arm? Or
Yeah, definitely.
Yeah, okay. That's an immediate description of friction. Or let's say you want to you've got a buddy of yours that's asked for you to throw something or slide something over to him. And you decide, okay, that's fine. I'm just going to push this along the floor and hopefully it'll get to him, if you're that concerned about it. And let's say you push it in motion. If you push it along carpet, what's generally going to happen?
It's going to slow down pretty fast.
But over time, what's going to happen to that object?
It's gonna slow down.
That's right. It's going to slow down because the force of the carpet is going to start rubbing up against that object. It's going to oppose whatever motion you're setting out. So you take the block, you're sending it over to somebody, the force of that friction is going to be pointing in the opposite direction. Tension force. So I've got a cord or a rope or something like that, and it's attached to a body. sake of argument here, I've got, here's my object. And got a string here or whatnot. This force that's applied right in here is going to be called tension. So a massless and unstretchable cord exists only as a connection between two bodies. Basically, that's the kind of physics problem we generally work with, is a massless, unstretchable cord. So it pulls, and what it's talking about here, if it's in between two bodies, then got something here, got something like that, and then we've got something that connects the two. So it's going to pull on both with the same force or the same tension. And this is true even if the bodies in the cord are accelerating, and even if the cord runs around a massless, frictionless pulley. And basically, we're looking at a way to simplify our assumptions as we go through this process. So the forces at the two ends of the cord are going to be equal in magnitude. In other words, pulling on this particular block is going to be the same as the block pulling on this particular cord against whoever's holding it. If we put in a pulley, the direction of that tension is going to change. So the tension is still being applied along the rope, because that's obviously the object that connects the two. But how that tension is being reflected here, we can see that the tension is the block pulling against the hand. And over here, this tension is going to be the hand that is trying to make the block move. If we apply the pulley in this particular case, we can see the tension going up here, and we can also see the tension pulling on this, and that's being pulled by the block itself. So let's take a look at 5.9c, this right here. So the suspended body there is going to weigh 75 newtons. Is T, the tension, going to be equal to, greater than, or less than 75 newtons when the body is moving upwards at a constant speed, at an increasing speed, and then at a decreasing speed? So again, let's draw the picture here. That way we're not having to look at it. And this is going to look horrible, and I apologize for this. So we got our box. And then we've got the pulley right here. It's attached to the ceiling. So if the body is moving upwards at a constant speed, is the tension going to be equal to, greater than, or less than 75 newtons? And again, that's your key word right there.
Equal to, because it's not accelerating.
That's right. It's not accelerating. So the tension is going to be 75 newtons. If the body is moving upwards at an increasing speed, then what is the tension going to end up being? Is it going to be greater than, or is it going to be less than?
If it's increasing its speed, then wouldn't it be greater?
Mm-hmm. Yep. Because you're going to have more force. And if it's at a decreasing speed, then it's going to be less than that. We go back and look at it here. So if it's moving up here, basically, if this is accelerating upwards, it's going to be pulling on that cord harder. And if it's pulling on that cord harder, guess what you're doing in order to pull it up faster? You're pulling harder and harder. If this thing is decelerating, in other words, it's slowing down, you're probably not pulling on it as hard. And that's why the force seems less than 75. All right. So Newton's third law. When two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. In other words, an action has an equal and opposite reaction. The same kind of thing you tell, your sibling whenever you're about to hit them because they hit you first. So when you write this law as a scalar or with vector relationships, this is how it's written as a scalar. The force from B to C is the same as the force from C to B. In vector notation, basically the vector that's pointing from B to C is going to be the same as minus the vector pointing in the opposite direction. So these are going to be considered to be third law force pairs. And anytime you have two objects interact, there's going to be a third law force pair that develops. So in the case where you've got a table that is sitting on the earth and you've got a cantaloupe up here, the force, let's see if I can blow this up a little bit. The force from the cantaloupe to the table, or the normal force from the table, is going to be the same as the gravitational force as the cantaloupe is trying to fall to the earth. And let's see if I can move this over here. So these are considered to be third law force pairs. So you've got the cantaloupe and the table, and the table and the cantaloupe, table and the cantaloupe. Those force pairs are equal and opposite. Okay, so suppose that the cantaloupe and table, figure 511, which that right there, are in an elevator cab that begins to accelerate upward. Do the magnitudes of the force of the table to the cantaloupe and the force from the cantaloupe to the table increase, decrease, or stay the same? They should increase. And the reason is that the table is having to push harder on the cantaloupe, and in return, the cantaloupe will start pushing on the table. Both of those will increase. Now, it doesn't necessarily mean that the cantaloupe's going anywhere, but it does mean that the magnitude of those forces are going to increase. Are those two forces still equal in magnitude and opposite in direction? Yeah, and they are. And do the magnitudes of those forces increase, decrease, or stay the same? And they begin to decrease slowly. The gravitational force of Earth decreases with height, but in the elevator, you're not going to notice that much. And are the two forces still equal in magnitude and opposite direction? Yeah, they're going to be that way. So we're looking at the magnitude and direction of forces of the table on the cantaloupe and then the cantaloupe on the table. And then here we're looking at the force from the cantaloupe to the earth, as well as the earth to the cantaloupe. That's why here these forces begin to decrease a little bit, because you're putting more separation in between them, because the elevator is accelerating upwards, getting further away from the earth. All right, so we got a sample problem here. So we've got a block of mass 3.3 kilograms. It's connected to a cord and pulley to a hanging block of mass 2.1 kilograms. And again, we have our magical frictionless surface here. If we go through and if we draw our force vectors, we see the normal force right here. And then we see the force due to gravity on this block S. Here we see on block H, we've got the tension of this being pulled up, and then we have the force of the gravity on block H. So if we draw the forces involved, we're going to treat the string as unstretchable and the pulley as massless and frictionless, and each block is a particle. Lots of assumptions going into this. And then draw the free body diagram, which is what this is about. So for block big M, or sliding block S, we have the tension of the rope being pulled this way. We have a force that's normal to this particular block. We have gravity, which is pulling on it this way. And if it is accelerating, it would be accelerating in this direction, because these two forces are canceling out in the y direction. There's only one force being applied in the x direction. That means the acceleration of that block must be this way. If we look at the free body diagram for block little m, we see the tension going this way, and we see the force of gravity going this way. If this block is moving this way, then this block has no choice but to move this way. For the sliding block, the tension is going to be equal to the mass times the acceleration, in other words, the net force. For the hanging block, the tension minus the mass times the gravity is going to be equal to minus ma. If you combine those, you find out that the acceleration is going to be equal to this fraction times gravity, and that the tension, once you take this and substitute it in here, you'll determine that this is the actual equation for the tension. So let's see, what else was it asking here? So if you plug in values here for m and little m in g, which we know to be 9.81 meters per second squared, we'll know what the tension is equal to 13 newtons, and then we can determine what the acceleration is here. It asks the question here, does this make sense? What if we'd got an answer here of A is equal to 10 meters per second squared? Would that have made sense?
No.
And why not? Reason being here is gravity is only going to accelerate to 9.81 meters per second squared, right?
Yes.
So if it's moving down, it can't pull that block any faster, or it can't accelerate that block any faster than that, right?
Yeah.
So if we'd got something greater than that, we would have known that something was wrong. Also, this value for the tension here needs to be less than the mass of the little block times gravity. So those are just some things to check in that particular situation. So we've got forces for a block being pulled up a ramp. We've got all kinds of forces being modeled here. I'm not going to go through all of that right now. So what we have here at the end, these are the summaries. These would probably be good things to go through, and I will have that information posted for you guys, so you can have it to look over. All right. Is anybody up for about a 15-minute break or 20 minutes?
Yeah, that's fine.
Okay. Why don't we go ahead and do that? I will stop the recording here, and if we can be back here at about 7:35, then we can go over chapter 6. Does that sound good?
Yeah.
Yep.
Okay.